So there's another extra method of mixtures, a little example I wanted to give here, to do with what happens if you add hot objects to liquid and that causes that liquid to evaporate. So we're looking again at specific heat capacity, but we're going to bring to that this idea of latent heat of vaporization as well. Latent heat, the energy required to change 1 kilogram of a material from one state to another. So in this scenario, we've got a jeweler, they're working on some copper. So they've got a little bit of copper here. Let's say they've got 100 grams copper, so 0.1 kilograms. And they're working on it, so it's pretty hot. I'm going to say it's 800 degrees C. Okay, and what they're going to do is they're going to pop it into a container, copper container, which has got again 100 grams, so 0.1 kilograms of water. But the jeweler's been using it a few times, so actually it's pretty warm already. It's already at 80 degrees C, and the copper container is 20 grams, so 0.02 kilograms of copper container. Both of these are at 80 degrees C. And so the hot copper is going to go in there, and some of the water is going to boil away. And the question really is, how much mass? What's the mass of the water that evaporates when the water and the copper container are both brought up to 100 degrees C? So what do we need to know? We need to know the specific heat capacity of copper, and that is 390 joules per kilogram per degree Kelvin. Specific capacity of water should be used to it by now, 4,200 joules per kilogram per degree Kelvin. And we also need to know the latent heat of vaporization of water, because some of our water is going to turn into water vapor. So that is just joules per kilogram. So that's the information we need to know. Okay, so the copper is going to go into here, and it's going to drop its temperature. It's going to go down to 100 degrees. Okay, so our energy lost is going to be MC delta T. Now, I noticed, I've realized that with the other videos, I was doing a bit of a shortcut here. This is a drop in temperature, so this should be a negative, which means this is a negative because it's losing energy. So when we do it, you can shortcut it, but just be aware that when you're working these out, if the object is losing energy, its temperature is dropping, then you should actually get a negative value for the energy because it's a loss in energy. As it is, the values are still the same, except you get a negative here because the object is losing energy, and you just need to be aware of that. And I was shortcutting it, and generally you do, but if the question gets complicated and you get a strange negative in there, you just need to be aware that's where the negatives come from. Because the temperature is dropping, you do get a negative value here. Anyway, so we've got the mass of the copper is 0.1. Specific heat capacity of copper is 390, and our drop in temperature is going from 800 degrees. It's going from 800 degrees, it's dropping down to 100 degrees, so it's falling 700 degrees. So we've actually, our energy is minus 27 joules. And like I said, it's a minus because the copper is losing energy, and the water and the copper container will gain that much energy. Okay, so the water's going up to 100 degrees and the copper can's going up to 100 degrees. So they're starting at 80. So the energy gained by the copper, energy gained by the copper, Cu. That's going to be mass times the heat capacity times by the change in temperature, but it's only going up 20 degrees because it's starting at 80 and it's going up to 100, at which point the water's boiling. It's not going to get any hotter than that because the water, that energy is now going into turning the water into vapor. So for our copper can, the mass of the copper can multiplied by the specific capacity of copper times by the change in temperature means our copper can is going to gain 156 joules. The gain in water, energy gained by water, that's going to be, again, mc delta theta, delta T. I should be really using delta theta for these, to be honest. Let's just change it. No, we'll leave it at T for now because this bit really it should be delta theta. Okay, so that's going to be the mass of the water is 0.1. Specific heat capacity is 4,200. And again, our change in temperature is 20, so our water is going to gain 8,400 joules. Okay, so in total, our system here, in going up in temperature up to 100 degrees, is going to get these two added together. So that's just going to be what? Let's call it energy total for raising the temperature is going to be 8,556 joules. Right, but the energy that's gone in is 27,300. So the rest of the energy must go into changing water into water vapor. So if we've got 27,300 joules going in, 8,556 joules is transferred, is raising the temperature of our water in our copper can. The rest, 18,744 joules, that's going to go into turning the water into steam. Okay, and water into steam, the energy is just the mass times by the latent heat of vaporization. Okay, so our mass is going to be energy over latent heat of vaporization, which is 18,744 divided by 2.3 times 10 to the 6 is the latent heat of vaporization of water, which is going to give us an answer. Just squeeze it on the end of the paper here. 2.15 times 10 to the minus 3 kilograms. Okay, so 18.15 grams of water will evaporate. Okay, and you can see we're looking at the total energy that's gone in. To start off with, that was the energy required to drop the copper from 800 down to 100. The water is going to be 100, and the copper can is going to be 100. That was the energy lost, and that equaled the energy gained by the copper can and the energy gained by the water to raise it up to 100 degrees, and the excess energy then we use our latent heat vaporization to work out that excess energy, how much water is going to get turned into water vapor. Okay.